Welcome to the most important application of first-order differential equations, which is the logistic equation. And what it is a better model for population growth compared to a previous one. Because if you remember, our basic model for bacteria growth was y prime equals 3y, which essentially says that the bacteria population grows exponential, y ce to the 3t. So if you start with positive number of bacteria, then it just explodes like that. It's y ce to the 3t. But to be honest, this model is pretty bad. Why? Because we can't really expect bacteria to grow indefinitely because the amount of food is limited. There's not an infinite amount of food that they can grow as much as they want. At some point, they will starve and their growth will be stunted. It's a bad model. Because amount of food is limited. Food is limited. And what we need is a better model for bacteria growth, one that takes into account the limited resources. Model that takes into account the limited resources. In fact, without further ado, here is the better model. But I do want to mention, by the way, so this is very typical in applied math. You first find a model, see how good it is, and then you critique it with the hope of finding a better model. So there's this constant interplay between having a model and improving it. Okay, so what is the logistic equation? At first sight, it looks very similar to before. So we still start with y prime equals 3y. But now we add, I guess technically we multiply this extra factor, 1 minus y over 20. And what do all those terms mean? Well, this number 3, that's what's called the growth rate. So just as before we had y prime equals 3y, where 3 was the growth rate. Here, the 3 is also a growth rate. And this 20 is what's called the limiting factor. Or carrying capacity. And I will explain it below what this means. Because essentially we will say the bacteria won't increase other than like over 20, because that's where the food supply is exhausted. And by the way, intuitively, this equation makes sense. Why? Because, well, if y is close to 0, so if we start with a small number of bacteria is close to 0, then this 1 minus y over 20 is close to 1. It's close to 1. And so our equation then becomes y prime equals 3y, which is our basic model. So with a relatively small number of bacteria, they will grow exponentially. But if the bacteria population is close to the limiting population, so if y is close to 20, then 1 minus y over 20 is close to 1, and then, sorry, is close to 0. And then basically 1 minus y over 20 is close to 0, and we get y prime equals 0. And that takes into account the slow growth of the population, close to the carrying capacity. But that is not why we're here today. What we're here today for is to study this as an autonomous equation based on the facts that I've mentioned in the previous video. Because notice, so upshot, this is in fact of the form y prime equals f of y, where f of y is 3y times 1 minus y over 20. So now, based on the previous video, what we want to do, we want to find where f is 0, where f is positive, where f is negative, because that gives us info about y. And I do want to mention we can solve this explicitly, which we'll do in a couple of videos later, but here we just want to do what's called a qualitative study. So let's first find what's called the equilibrium solutions. Solutions. What does equilibrium solution mean? It means constant solutions. So here, we just need to figure out when f is 0. So this just means again, that's literally the definition, f of y equals 0. So let's do that and see what we find. So f of y equals 0. That means 3y times 1 minus y over 20 equals 0. But then remember, if the product of two numbers is 0, either the first one is 0 or the second one is 0. So we get 3y equals 0, or 1 minus y over 20 equals 0. And that tells us either y is 0 or y is 20. And so based on what I talked about before, this means we have two constant solutions, 0 and 20. So y equals 0 and y equals 20 are constant solutions. But then, more interestingly, what does that mean in terms of our model? It means that, well, if you start at 20 bacteria, you will end at 20 bacteria. So it's kind of the Vegas of solutions. If you, whatever happens at 20 stays at 20. If the population starts at 20, it stays at 20. So we can draw this on a graph if you wish. So again, we have two constant solutions. Y equals 20 20, and y equals 0. By the way, it makes sense. Well, if you start with no bacteria, there's no way of them for growing, so it stays at 0. But if you start at 20, essentially, they already ran out of food, so they can't grow any further. That's why it stays at 20. But now the question is, what happens in between? And this is where what's called a bifurcation diagram can help us. Because remember that fact, whenever your function is positive, the solution is increasing. Whenever the function is negative, your solution is decreasing. And that's what will help us. So draw a bifurcation diagram. And turns out this is exactly the same thing as that sine table that you use in calculus to draw graphs. So how do you do it? On the left-hand side, you draw y and all your equilibrium solutions. So minus infinity, 0, 20, infinity. And then on the left-hand side, you draw all your components of your differential equations. So we had a 3y, we had 1 minus y over 20, and then the product, so y prime, which was 3y times 1 minus y over 20, and then your function. So let me repeat. You first draw y, minus infinity, infinity, and your equilibrium solutions, 0 and 20. And you put all the products. So we had 3y, 1 minus y over 20, the product, which is y prime, and then y. And then you just figure out the signs. So if y is between minus infinity and 0, 3y is negative. And then if y is between 0 and 20, it becomes positive, and then positive. And here it's 0. And then let's continue with 1 minus y over 20. Well, if y is negative, minus y over 20 becomes positive. So this becomes positive, and then it switches to negative. No, never mind, sorry. Still positive between 0 and 20, because throw out like 1. 1 minus 1 over 20 is positive, and then it switches to negative. Negative. And then you just multiply everything out. So minus times plus is minus, and then it becomes plus, and then minus again. Plus, minus, and then 0, 0. And then last but not least, well, remember, if y prime is negative, then y is decreasing. And if y prime is positive, then y is increasing. So essentially, what we get a decreasing solution, increasing, and then decreasing. Now, what does that mean in terms of our solution? So maybe let me draw that side by side. So remember, we had our two equilibrium solutions. So we had our 0, and we had our 20. Y equals 20. So y equals 0 and y equals 20. And remember, all this is based off y values. So it says that if y is below 0, so if it's between minus infinity and 0, then actually y is decreasing. So if for some reason you had a negative number of bacteria, it would just go down. Of course, not reasonable really in terms of our application. But now this is really saying that if the bacteria is between 0 and 20, then the number just increases. So it might start like this and then increases like that. And last but not least, if the number of bacteria is above 20, then it just decreases. It goes down. And there you have, sort of a qualitative graph of our solutions. So roughly, this is how the bacteria evolve. If it's below 0, it'll just decrease. If it's between 0 and 20, it'll increase. And if it's above 20, it'll decrease. Which makes sense because if there's too many bacteria, more than the number of food, it will go down because they all die out. But if there's not enough bacteria, they will grow until they reach this carrying capacity. And by the way, notice, well, this y equals 20, solutions seem to go towards it. This is what we call a stable equilibrium. So note, we say y equals 20 is a stable equilibrium. And all this means is that nearby solution move towards it. Towards it. On the other hand, y equals 0, notice solutions move away from it, and that's what's called unstable. Is an unstable equilibrium. And I'll show you a direction field very soon, but again, the interpretation is if the bacteria population is above 20, it will die out. Due to limiting resources. Until it reaches 20. And if it's between 0 and 20, it's between 0 and 20. 20. They will multiply until it reaches 20. Right. And I do want to show you really cool pictures of real life evidence of this. So let's see, 350 lecture 4. No, sorry, lecture 3. So first of all, I wanted to show you a direction field of what this looks like. This is a nicer picture of it, but really, first of all, the direction field confirms our guesses. So between 0 and 20, the population goes up, and above 20, the population goes down until it reaches 20. And what I want to show you is this really cool thing, because, I mean, not bacteria, but population of but population of Belgium, actually. So notice that if we just did the exponential model, we wouldn't be able to fit those dots. But if we use a logistic model, then it fits the points much more nicely. Sorry, that was for bacteria. And now for population of Belgium, I just want to show you how beautiful a logistic model fits the data, because the dots is a population of Belgium between 1980 and 2000, and just look how the logistic model fits it so nicely. All right, so that's all to know about the logistic model. In the next video, I'll do a more practice example with qualitative diagrams.